So, deducing a rate law from initial rate data. So what you need to be looking for is how the rate of reaction changes with respect to one or the other, the reactant. So your rate law is going to take the general function that the rate is equal to the rate constant K times the concentration of one reactant raised to the power of whatever the order with respect to that reactant is, multiplied by the concentration of another reactant raised to the power of whatever the order of reaction in with respect to that other reactant is. So the way to determine this experimentally is look at your data. The initial rate has been recorded with concentration of each of the reactants. So you're going to look for where the concentration of one reactant has been held constant and the concentration of the other reactant has been allowed to vary. Therefore, the initial rate of reaction is only depending on one reactant. So in this case, our initial rate is only depending on the concentration of dihydrogen. So what you can do is you can use the ratio method where you take the ratio between the rate of reaction between experiment 1 and 2 in this case, so rate 1 over rate 2, and that is going to be equal to the same ratio between concentrations of, in this case, hydrogen raised to the power of whatever the order of reaction with respect to hydrogen is. So that'll be for the initial rate for reaction 1, and this will be the initial rate for reaction 2, and all of that will be raised to the power of, let's just call that m because we're doing that one first, okay? So let me just draw some parentheses to clear that up a little bit. So this should obviously be in parentheses here. Sorry, they are ugly. And then that will be the ratio, so it's divided by. So let's go ahead and work this out. So I'm actually going to do experiment 2 over experiment 1 just because numerically experiment 2 is the larger number, but you could do it either way around. It's going to make sense either way. So I'm going to do 2.67 divided by the 0.619. We'll worry about units in a minute. At the moment, we're just doing ratio, so it doesn't really matter. And that will be equal to that initial concentration of 4.96 for experiment 2 over 2.39 for experiment 1, and whatever that shakes to be out to be is going to be raised to the power of m. So let me go ahead and just draw some lines so it's clear that we are dividing there. So let's do the mathematics on this, and sometimes you'll get like a nice even number, which is great, and it's really clearly like, oh, 2 equals 2 to the power of n. What is n? N must be 1. But sometimes you won't get that, right? Sometimes you'll get a less fun number. So let's see, I get 4.34 on the left-hand side equals 2.08 to the power of m. So to get rid of m to the power of m, we're just going to do log of both sides, okay? So log of 4.34 equals m, and then log of 2.08. So then I can divide both sides by the log of 2.08 and solve for m, right? So m will be the log of 4.34 divided by the log of 2.08. So then we can solve for m, and that is just going to turn out to be 0.64 divided by 0.32, which is just going to turn out to be 2. So the reaction is second order with respect to the reactant that the concentration has been changing. So that was with respect to hydrogen here. So second order in hydrogen. So second order in concentration of H2. So then we're going to rinse and repeat for our other reactants. So I'm just going to scrub this off. So what we're looking for with our second reactant is, again, we are looking for now where the concentration of hydrogen is being kept constant. Let's just pick a different color here. And the concentration of nitrogen is being allowed to vary. So experiment 1 and 3 is where the concentration of hydrogen is being kept constant. So when varying the initial concentration of nitrogen, so we can solve for the order of reaction of nitrogen, we're going to be comparing these initial rates of reaction. Okay, so let's do it. So we're going to do a ratio between rate for experiment 3 and experiment 1. So I'm going to do rate 1 over rate 3. So 0.619 divided by 0.2 0.229 for the ratio between the rates, and the concentration of nitrogen, let's see, for experiment 1 was 0.112, and for experiment 3 was 0.0415, and that will be raised to the power of whatever the order of reaction is with respect to nitrogen. So let's just draw a line on here so we can see what we're doing. So we're just going to stick that in our calculator and solve for n. So terrible, ugly brackets. 0.619 over 0.229 I got is 2.70. And then let's see, that is going to be 0.112 divided by 0.0415 is also going to be 2.70, and that'll be to the power of n. So you might just look at that, but like, hey, n's got to equal 1, so it's first order. But you can also go and do the log of both sides. So log 2.70 equals n log 2.70. So then take the 2.70 to one side, log 2.70 divided by log 2.70. Well, the same thing divided by itself will equal 1. So n equals 1. So it's going to be first order with respect to nitrogen. Where's my line? There we go. There's my line. Okay. So text. So first order in concentration of nitrogen. So then we can use that general form of the rate law to write ourselves a rate expression. So rate equals K times the concentration of nitrogen raised to the power of 1 because it's first order, so you don't have to put in anything there, and then times the concentration of H2 raised to the power of 2 because it's second order in hydrogen. So that would be your answer for that first part. Then it asks us to solve for K. To solve for K, you are going to just plug numbers into the rate law from one of the experiments. So pick a line, 1, 2, or 3 in the table. You've got to be consistent, apples to apples. Doesn't matter which one you pick, okay? And you're going to rearrange and solve that rate law for K. So making K the subject, then K is going to be the rate divided by the concentration of nitrogen times the concentration of hydrogen. Remember, that is squared. Be careful when you do this because your units of K will depend on what the orders are in your reactants. It will actually change the units of K. It depends if your first order in both reactants or first order in one, second order in the other. It'll make a difference, right? So let's substitute in then. So K is our rate. I'm going to just do experiment 1 because it's right there. So 0.619, and that is units of molarity per second, divided by the concentration of nitrogen, so 0.112 molarity, times the concentration of hydrogen, 2.39 molarity, and that is squared. So be super careful with your units there. So if you stick that into your calculator numerically, you should get what I got, which was 0.9676, blah, blah, blah. We're asked for 2 sig figs, so 0.97. What about the units? So if we look at the units, we can see that molarity is going to cancel here and here. So we'll end up with per second per molarity squared. So molarity to the -2, seconds to the -1 would be my units. Okay, and that is the method that you need to follow through for deducing your initial rate law your rate law from initial reaction data. So just you've got to find experiments where the concentration of one reactant is fixed and the other reactant is varied and the rate measured. So you can work out the order with respect to the reactant that's concentration was being varied. Repeat for the other reactant, and then you can use that to construct your rate law. All right, hopefully that is helpful.